Okay, so thank you everybody. Also, I mean, it's the last talk of the workshop, so I mean, it's quite so. Thank you for inviting, and I mean, hopefully this is going to be interesting. The topic is probably a little bit different from what have been discussed in these days. At least the application is different. The class of methods is the same, but the application is extremely different. So therefore, also the way you actually implement and use these methods is different. Okay, so we'll see probably something that I mean is not precisely on the line, on the style of the presentation that have been done so far. This is a work that I'm doing since May with Freddy Bouchet at ENS-Lyon, and also in partial collaboration with Jeroen Wouters, because this was an AXA-funded project. AXA is an insurance company who has a private research fund to fund postdoc positions, and this is a project that originally was started by Jeroen. Then Jeroen went to work on another project, and I stepped in, and then actually I did this part of the work while he focused on another one. Okay, so the idea is to use algorithms that have been developed in the framework of large deviations, and that partially have been also discussed in these days, to sample in a very efficient way, or at least in a more efficient way with respect to a brute force approach, the extreme events, or at least the tails of a distribution of an observable of a dynamical system. And to apply these methods to a simulation with a numerical model of the climate, okay? Which is a quite more complex object than a simulation of turbulence, typically, because there are a lot of physical processes entering in the system. There is much less control on the equations also, and on the physics of the system, and these are very heavy technological objects, and so it's really difficult to sample extremes efficiently. So the idea is to see if the techniques that have been developed by your community could be applied to a case like this, and we will see if this makes sense or not. Okay, so as I was saying, climate science, I mean, more or less everybody has an idea nowadays of what is going on, and the fact is that it has become quite fashionable in the past 20, 30 years because of this problem of global warming. One of the main applications of trying to reproduce and predict the future climate state is about studying the statistics of the so-called extreme events, so events that are very rare and connected with large anomalies of a certain control variable, which could result in some hazard and some risk condition. Example of extremes are, I mean, this extreme means nothing, I mean, everything and nothing. You can go from, you have a really wide range of phenomena that can be described in this way. You can go from very localized events like, I don't know, a few years ago there was a very big storm over the city of Genoa in Italy, in which in 6 hours it rained what normally, like half of what normally rains in 1 year. So that was a very localized event in space and time. And on the other side of the spectrum, you have something like the heat wave that went over Russia in 2010, in which it is an event that lasted for 2 months and spanning like, I mean, quite a big geographical area. So, you know, very different spatial temporal properties. In general, the problem that we have with these events is that they are extremely rare. So first of all, we don't have the data. Because simply we don't have the data. I mean, we have reliable data from the 50s. That's the really reliable data from the 50s. The really reliable data, in particular on certain observables like precipitation, are from the 70s. Before that, we don't have them, okay? Or at least they are very bad. And we have to reconstruct them with the aid of numerical models. So we have few data. The second problem is that because there is a global warming, the time series of these observables normally are non-stationary. So it's already difficult to find the probabilities of very rare event when you have a stationary process. If you have something that changes in time, it's almost impossible. I mean, it's crazy, okay? So it's very difficult to work on data. So you have to rely a lot on numerical simulations. The problem with numerical simulation is that if you, as I was saying, these climate models are very, very heavy object, and if you want to have, a model that is physically reliable, then this is very costly to run and takes a lot of time. And again, you have a problem of building up a sample of enough size to make a reliable statement about the probability and the return times of this event. So the idea, so we need some smart computational strategies to sample the extreme more efficiently, which is more or less what some of the people here have talked about. And so we want to see if this is possible. Specifically, I say it in advance, we were going to use an algorithm, let's say call it population dynamics algorithm, that have been briefly discussed by, extensively discussed by Takahiro yesterday. And I will recall the idea of the algorithm, and in particular in the practical aspects of really what you do when you, in practice, when you compute stuff with that algorithm. Okay, and which is the application? Okay, we define one extreme we are interested in, and we work on so-called heat waves. Heat waves are anomalous periods of high temperatures over an extended area by institutional definition from the World Meteorological Organization. You read it there. It's basically an anomaly on the average maxima, on the average daily maxima. The two most, let's say, the two strongest events in the recent years have been the European Summer of 2003, that people may remember, and as I said already, the Russian heat wave of 2010. This is a picture from these are anomalies of temperature with respect to the climatological average, probably average over the time life of this heat wave in 2003. Consider, for what I was saying before, that most of the studies you find in the literature post-2003, which are about the physics of this event, so why this event occur, are case studies based on this event, one event, okay? Just to say which are the problems. Of course, it's difficult to establish correlation to understand physical processes if you have one case study of that event. So this is the conditioning we have to work.
So may I ask you,
yes?
Why it's called waves? Waves is something like that, plus minus. Here just plus.
Because it comes and it goes.
Yeah, basically, yes. More or less, yes. And because it's connected to a very specific weather pattern, which is called blocking, which is basically it's something that comes, stays for a while, and go, and it's connected to a specific dynamic process, which is basically, okay, you maybe remember yesterday what Freddy was showing about this circulation at the mid-latitudes. He shown a video of this jet stream. It was this pattern of very strong winds quite high up in the troposphere, which is like one of the dominant mode of variability of the mid-latitudes. Blockings are these weather patterns that are connected to heat waves, are basically a deepening of the meanders of the jet stream. Here in this picture you see the contour lines. I'm sorry, the picture is not very good. The contour lines are the 500 hectopascal geopotential height that you can look at it like as a string function, essentially, and so this is essentially the jet stream, okay, that pattern that Freddy was showing. And the colors are the anomalies with respect to the climatological average. So here you have an anticyclonic anomaly, and here we have a cyclonic anomaly. What happens is that sometimes you have a deepening of these meanders of the jet stream, and you have a strong anticyclonic anomaly that sits over Europe. You have similar things on the US and other land masses, but let's say about Europe. The strong anticyclonic anomaly that sits over Europe and stays there and inhibits cyclonic anomalies to pass through. Okay, then it stays there for a while, and then it moves away, but for the time it stays there, this leads to a strong increase in the temperature. Essentially because, as also Freddy was mentioning yesterday, in geophysical flows, anticyclonic anomalies are connected to upwards motions, that's the reason why it rains when there is a cyclone passing. And anticyclonic anomalies are connected to downward motions. And when you have downward motions, you are inhibiting essentially condensation of water, so you have clear sky conditions, and when you have a persistent situation of clear sky condition for a long time, you have a lot of incoming solar radiation, and this increases the temperature at the surface. This is the basic mechanism, okay? Okay. To go a bit more into details, people have classified heat waves taken from observational data set, what you can do, and they have seen that over Europe you can basically classify 6 patterns, okay? They call it the Russian pattern, Western European, Eastern European, Iberic patterns, this North and something, okay, and this Scandinavian cluster, in which, anyway, in which they are quite well separated, in which basically in each case you have the anticyclone in different positions and the temperature anomaly directly below the anticyclone. These are composite averages over these heat waves events. For some of them, it's also important the hydrological preconditioning, meaning the state of the soil, how much moisture is the soil, but that's not important to go into details. So the thing to say is that in Europe, large fluctuations of temperatures are connected to very specific dynamical structures. So it could make sense to use these algorithms to capture these fluctuations, because we could try to use algorithms that lead the system to realize these dynamical patterns. Okay, so this is the idea. Okay, so okay, this of course is something that everybody knows here, but just, okay, so since these algorithms have been developed in the large deviation framework, I define a few things. Okay, I consider a process, which in my case is the state of the climate evolving, and I consider a time average of a certain observable, which in my case would be, for example, the area average over Europe of the surface temperature. And I consider the average over a long time, and then I say, okay, I'm in a large deviation framework when the probability of this average scales in a certain way with t. So my large deviation parameter is the observation time, and then I know I have a rate function which tells me how the shape of the distribution is. And I know that this, in this regime, is connected to the scale cumulant generating function via Legendre transform. Fine, this is the basic thing. So how this framework could be useful to study those events? In general, I could think that, I could use it as a statistical framework. So for averages long enough, I have a universal behavior of the distributions, and I can use it to study these processes. One has to pay attention by, how long has to be this time t with respect to the characteristic time scale of the event. And in particular, if you take the surface temperature average even over a small area, this has a correlation time of about 1 week. And heat waves are objects that have a lifetime of about 10 days, 2 weeks maybe. So definitely I'm not in the large deviation limit for the individual heat wave.
But if this anticyclone, the rotation period, what is this typical period of rotation inside the cyclone?
This I have to say I don't know.
Be many rotations would be your large parameter.
Yes, but the point is that I'm interested in the fluctuation of the temperature. So what I'm interested in, my relevant time is the time the anticyclone stays there before moving away. So it's not really the rotation period of the anticyclone.
Still, I would check it, because generally in Earth's atmosphere, it's not a Jupiter. We don't expect long-living vortices.
No, exactly.
And blocking is a long-living vortex.
Relatively long-living.
It's not a stationary solution of any equation that
No.
long ago with Kuznetsov shown that it could not be. So it's somehow fed by something. But I think that the period of rotation is a relevant parameter.
Okay.
I would check
Okay.
how
Yeah.
many periods it rotates before it moves, it disappears.
One other thing I will say at the end is that one of the things next phase is to make a better analysis of the statistics of these events. So this is one of the things that could be done definitely. Okay, the point. I'm not saying that a heat wave is an event that is per se in the large deviation limit, but I'm saying that I could use some of the methods that have been developed in order to get the tail of the distribution. So therefore, looking at a way to optimize the estimate of the tail of the distribution of a very, very long average of the surface temperature, with this population dynamics algorithm by basically forcing a train of heat waves. Okay? So a sequence of heat waves that then will lead me over a long time to a large anomaly of the temperature. Okay. So the method that we want to use is this population dynamics algorithm that has been introduced yesterday by Takahiro, and here you can find the references to have details about the math behind it. Basically, it works in this way. So you make an ensemble simulation of the system with.
The equation of the system, what are?
The equation of the system I explain later, if you don't mind. Let's say you have a numerical model of the climate. I will explain about what kind of model. You use the model as a black box. This is actually what I was asking yesterday. So you don't care about the equations of the model, okay? You take an ensemble of n trajectories. You run the system, and for, let's say, each of them for a time t. And then, periodically, every time tau, that I call cloning time, you perform a killing cloning procedure of the trajectories. So what you do is that you assign a weight to the trajectories that basically goes exponentially with the average of the control variable in the time window between the preceding cloning event and the actual cloning event. This R is just the sum, just the average of the weights, so this is just a normalization. And then you say that each trajectory will produce a number of copies of itself which is proportional to this number. If this number becomes less than 1, the trajectory is killed. Okay? And then there is some technicality on how to keep the number of trajectories always n, but this is not important. So essentially, yes? The system is deterministic? They have developed it for non-deterministic systems, for stochastic systems. If the system is deterministic, you have the problem that you have a little bit, a small perturbation. No, but this is quite a problem, actually. You put to decide how to do it. You put a small perturbation such that the trajectories will separate, and then you have independent, they are not independent, they don't have to be independent. They have copies that are not identical to each other. So the idea is that then, tuning this value, this parameter k star, you are selecting trajectories that are realizing large values of the average of your control observable. And so basically you are moving the system towards the tail of the distribution. Okay, so basically, if you want, you would have a normal ensemble simulation. You would have one realization doing like that, one realization doing like that, and all of them would realize a certain distribution of your system. What you're doing now with this method is that you are forcing the evolution of the system to do something like this, and therefore to be clustered around the tails of the distribution. And the idea is that then you have formulas to compute the statistics of this distribution, which is the real one, using this one, in such a way that you are making the actual computation in a world in which you have a lot of data on the tails. And in this way, you can improve the precision on the estimate, because you have the data. Okay, this is the idea. Okay, and so the first thing you can compute very directly, you can compute the scale cumulant generating function in k star, where k star is the value of k that is being used to bias the simulation, because you can see that the generating function is basically, it becomes the product of the normalizers, and therefore the scale cumulant generating function becomes essentially the time average of the logarithm of the normalizers of the weights. Okay, so, and this is a very direct computation, and the method is meant to compute in an optimal way lambda of k star, in the sense that it should be unbiased estimator, and it should work very well to compute the scale cumulant generating function in k star. But as I said, in general, we have also an idea of how to connect expectation values computed on the normal dynamics to expectation values computed in the bias dynamics. And we can do it in this way. Essentially, you have a weight of the path measure of the system, such that you can compute expectation values in one universe and expectation value in the other one and go back and forth with each other. Just as an example, and in this way you can compute a scale cumulant generating function for any value of k, you can compute rate function, you can compute whatever you want. Just as an example, if you want to compute a scale cumulant generating function for any value of k, then you apply this formula and you get these results. So basically it's the scale cumulant generating function in k star plus a correction, which looks very reasonable, the form that he has, as you can see. You're basically shifting everything around k star. Only thing to pay attention is that the expectation values on the bias dynamics are a bit tricky to compute, because basically you have to reconstruct the effective ensemble of the trajectories that have survived from the beginning to the end. To explain very briefly, let's say that you have 3 trajectories. So one was going like that, one was going like that, one was going like that. Okay? And then here you have your cloning event. Okay, this was going, let's say that you wanted to target this part of the distribution. Then this trajectory was going in the wrong direction. This is killed. This, let's say, continues. And this will produce 2 new trajectories. Okay? When you compute the ensemble average over the bias dynamics, you do it over an equivalent, an effective ensemble that is done like this. Okay? So you have cancelled the failed history of this trajectory. Note that, and this is something that Takaya was referring to, maybe like this is a bit more clear, you have the problem in this way that a lot of trajectories, in particular where k is very large, will have large parts of their past histories identical. Because you see, these 2 trajectories from here to here are the same. So it could be, in particular for large values of k star, that you need a lot, I mean a very large ensemble, because even with the reduction of the effective number of trajectories, then you still have a decent number of trajectories to compute expectation values as ensemble averages. So it's a bit tricky, but this is more or less the way it works. Okay, so we want to apply this algorithm to a general circulation model. The model that we have used is called Planet Simulator. PLASM. It has been developed in the University of Hamburg, where I did my PhD. It's essentially it's a numerical model of the climate that is representative of the complexity of the state-of-the-art operational climate models that are currently used to make, for example, the IPCC reports. But it's run with simplified settings. So let's say that it's basically a climate model that was competitive at the beginning of the 90s. Okay, this is essentially the type of model that we are using. I explain a bit how the model is done in the next slide. But first I want to say how we want to proceed to test if this method can be used. We take as indicator of heat wave, a very simple one, the area average of surface temperature over Europe. Okay? And then we perform a very long control run of 1,000 years, and we compute directly, brute force, scale cumulant generating function and rate functions. Okay? This is quite a big effort. This is about is a bit more than 20 days of simulation on parallel computing and everything. Okay? So this is kind of heavy. In this way, I can compute in a reasonable range of values the details, basically, of the rate function. And then I do a series of experiments with the population dynamics algorithm using a number of clones. Each of them run for a certain amount of time, such that the total computational cost, so the length of the simulation times the number of clones, is smaller than the length of the control run. And then I show that with this smaller amount of data, I have the same or even better performances than the brute force approach with the very long simulation. Because, of course, I have no clue about how the rate function and the scale cumulant generating function really are. So first I have to compute them directly. And then I check that using less data, I have the same performances in estimating this quantity. And then it means that the method has worked. And then I can think to use it then to study the statistics of the events that lead to those large anomalies. What is the model? Okay, the model is, this is a slide that you are obliged to put when you use the model, just to make advertisement of it. Is essentially a spectral model of the atmospheric circulation, in which basically you have the conservation of momentum. So basically you have the Navier-Stokes equation in hydrostatic approximation, plus the first law of thermodynamics and the equation of state to connect temperature and pressure and therefore velocity field. The model contains a lot of processes which are not resolved on the resolution of the grid. And in the case of the climate, this is the big problem, because you have a lot of processes about which you have absolutely no clue how to write them down as equations, for example, properly at least. Like you have, for example, the deep convection, so the convection that happens in particular in the tropics, and the consequent phase transition of water, so, and then the release of latent heat due to the condensation of water. This has a lot to do about the microphysics of what happens inside the clouds, how the droplets form. It's a terrible mess. There are simplified models of these processes, which are called parametrizations, which actually take most of the computing time of the model, that you have to introduce. Essentially, what is introduced in this model is relatively simple, is convection and therefore phase transitions of water, and the interaction between radiation and the atmospheric fluid, so the radiative transfer part. So absorption of solar radiation and absorption and emission of long-wave radiation, essentially. Then there are some modules that are switched off now, so there is no vegetation is normally used for paleoclimate studies, is not on. And the sea ice, which is very difficult to represent, and the ocean are set as fixed boundary conditions, as I'll explain later. So how is the setup of the model? The model is set up in, well, it's called T42 resolution, because the model is expressed in spherical harmonics. So this is a truncation in the spherical harmonic space. This corresponds to in physical, let's say, in physical space, to a resolution of 64 grid points in the latitude and 128 grid points in the longitude. 10 vertical layers, so we are talking about 10 to the 5, 10 to the 6 degrees of freedom. So it's a kind of a big system. Boundary conditions are set in this way. We don't want a time-dependent forcing acting on the system, to simplify things. So we remove the daily cycle, which is not a big problem because the model runs without the daily cycle anyway, and we remove the seasonal cycle. Okay, so we do a kind of experiment which is a standard in the literature to study processes that occur in a specific season, which is called perpetual summer simulation. So you fix the incoming solar radiation and you fix the surface temperature of the ocean to the climatological value for the 16th of July. The surface temperature on land is free to evolve.
What is
okay.
the time?
It's half an hour, time step of half an hour, 30 minutes, which is the minimum you can have with this kind of resolution. Like the biggest climate model work with a time step of 5 to 10 minutes. Okay, so then we do our control run of 1,000 years, and what we have is a ridiculously warm mean state, which is of course not realistic, but we don't care, because thanks to the fact that the surface temperature of the ocean is fixed, more or less the circulation, which is this is the climatological average of the 500 hectopascal geopotential height, is more or less what you observe. So the dynamics is more or less okay. The absolute values of the temperature are very high, but okay, let's say that for now it is okay to play with a system like this. And our control variable is the average of the surface temperature over this area. I have cut this part of Europe because I didn't want to mess up with the anticyclonic anomaly that often occurs.
It's not the instantaneous, it's the average over five days. The control
The control variable is the average over a long time, which long depends, I will show it later. No, it's the average. It's the average over time. I've cut this part, which has not maybe been a good idea because I didn't want to mess up with what is happening in the center of Russia. But it could have been, as we will see later, it could have been better to include that part as well. To reply to your question, first of all, we compute the scale generating function and the rate function with the direct method. So the method we have used has been like, there is a paper of Rauer and Angeletti and Touchette, which is still a archive paper, in which basically they show that to compute the rate function in a nice way is actually better to first compute the scale generating function and the derivative of the scale generating function with a block averaging method, and then through Legendre transform compute the rate function. And it's actually, we have seen that this is true. You get much smoother estimates and with more stable estimates. The length of the time, this is the minimum time for which I am in the large deviation limit. So for which the PDF in which the PDF start scaling with t with the rate function. And this, as we have seen, is about 2 years, which is incredibly long if you consider the autocorrelation time of that observable is about 7-8 days, because the autocorrelation function has a very, very, very slowly decaying tail, basically. So the time it takes for the integral to converge to 8 days is actually 2 years. So, this has been computed in this way. So here you have the scale cumulant generating function. Here you have the rate function. The blue line is the estimate. The magenta line are the Gaussian fits. So you can see that it's, in particular, for the positive anomalies, these are quite Gaussian. This black line indicates the range of convergence of the estimator. In this paper, they propose also ways to estimate the range of convergence of the estimator. So we know that up to here, the estimate is reliable. Outside, no. The error on the estimate is actually properly defined only of half this range. Okay, so we have error bars between 0 and 2.5, and consequently also here. But we will show the error bars later. Okay, so we want to reproduce this thing with the population dynamics algorithm using less data. So we take 128 trajectories, each run for 800 days. So it's about the 2 years that I have used to compute the direct estimate, but accounting also for a little transient, which means computational cost of 1/4 of the 1,000 years. Okay, we take the initial condition from the control run. We take a cloning time which is equal to the autocorrelation time of the observable, because we have done tests with the Ornstein-Uhlenbeck process in which we have the analytical solution, and we have seen that in that case, the autocorrelation time is the optimal choice to compute these quantities. Of course, this system is not an Ornstein-Uhlenbeck process, so there is no reason to think that it will be optimal. It's just a first guess because we have to start with something. And then, as you were saying, we have to add some noise, some perturbation after the cloning time to separate the trajectories. And this is done adding spatially uncorrelated Gaussian white noise over the surface pressure with in a multiplicative fashion. So it's a 10 to the minus, it's a relative, with a relative magnitude of 10 to the minus 4. This is basically because it's what they do when they create the initial condition. So when they create the initial condition of the model, they take a zonally symmetric state for the temperatures and for the variable, and then they give this little kick to the surface pressure, and then this develops the dynamics. So I relied on what is already done to do a similar thing by the model itself. Finally, we get to the results. So I still have some time. Yes. Okay, so as I said, the first thing you compute is the scale cumulant generating function in k star, basically as the time average of the logarithm of the normalizers. And this is the time for a case k star equal to 3. So here. this is a time series of the normalizer, and you see that after a transient period, this quite nicely jumped to a new state, in which the logarithm of the normalizer correctly oscillate around the value of the scale cumulant generating function that has been obtained in the direct estimate method. So it makes sense. Before going more quantitatively about it, it's interesting to see how is the climate in this part of the evolution and in this part of the evolution. In this first 80 days, in this first transient period, we have a certain pattern. This is the average over the winding trajectories. So this is the climate of the bias dynamics minus the climatological average in the normal run. So these are the anomalies with respect to the real world. What you see is that the new state, the one that correctly computes the scale cumulant generating function, is qualitatively very similar to one of the patterns that I showed at the beginning about the heat wave pattern. Specifically, this is what would be called the Scandinavian heat wave. We have a strong anticyclone here, sitting on top of Scandinavia, with a large temperature anomaly. And this is essentially in a blocking state. So what does it mean? This is the average. This is the climate of the bias dynamics minus the climate of the unbiased dynamics. So it's really true that the system, in order to realize this large fluctuation in the temperature average over a long time, is realizing a climate in which having heat waves is normal, which is exactly what I want. So it seems that it makes sense that I'm getting these dynamical patterns. Of course, this is, just a very qualitative view, just to have a first idea that things are going in the direction we want. Going more quantitatively, this is the scale cumulant generating function. The blue line is the direct estimate. The red line, the red points are the estimates obtained with the population dynamics algorithm for using k star equal to 2, equal to 3, and equal to 4. And these error bars are very naively computed from the variability of here, so just 2 times the standard deviation of this time series divided by square root of n. And the red lines are the estimate of the scale cumulant generating function for any value of k using those formulas about the expectation values, using the data coming from each of these experiments. And we can see that the agreement is quite nice. We are indeed able to reproduce the scale cumulant generating function. And in particular, we are outperforming the black line, which is the direct estimate on the same amount of data that would correspond to one of the Jordan apportion arguments.
How much does it depend on the number of clones that you have taken initially? Is it slowly converging?
I've not done a sensitivity on the number of clones. This is the next thing I have to do. Absolutely. And the idea is that the larger you want the value of k star, the more clones you will need. With these values that I have taken, it's 128 clones is enough. Apparently is enough. But how this scales, you have to make the experiments and see. This is the next part. Now the next part is going to be the sensitivity of the algorithms, and this is one of the things I will do. Then we can look at the rate function computed in the same way, and we have basically the same result. Yes?
Because people might say, if you do the brute force, you have everything.
Yes.
And you don't have to make any optimization of any new algorithm, right?
Right.
You have not only the statistics for these particular events, but for the whole field, right? While in this way, you are outperforming the prediction of this event, but you are completely blind about the rest of the dynamics.
It is true. This is true. The point is, the idea is that if we are able to push this method to really sample very, 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 very rare events, then it could be that we are computationally more efficient. But this depends on what we want to look at. There will be cases in which making 300 years of direct numerical simulation would be enough to do what we want to do. This depends. It's not that we can use it for everything. It will depend on the question we are asking. Also consider that here, I'm not yet computing the very, 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 very rare events, because the largest values of rate function that I'm estimating correspond for a t of 2 years at a range between 5 and 1%. So I'm not, I mean, I'm in the tail of the distribution, but I'm not really in the far, far tail. But this for me was just to, because I mean, I have to start slowly because the system is complicated. So I have to start slowly and I have to check the thing work. You know, trying to reproduce what I'm sure I am able to compute also with a direct simulation, because if it fails here, then it's pointless to try to extend it. The idea is that if it works here, then I can go further, and the idea is that I could try to reconstruct piecewise the rate function, basically by taking increasing values of k star, and as long as the estimates overlap, I'm allowed to say that I'm exploring far and far more from farther and farther regions of the tail of the distribution. Very briefly, because I think I don't have much time. Now the point is to make sensitivity, because this was really like the first attempts. To make sensitivity, the sensitivity are basically 3 things: the number of clones, as you were saying, the intensity of the perturbation that you put to separate the trajectories, and the length of the cloning time. So this is just to show that, or we already have problems when we change one of them. This is in a case in which I've multiplied by 10 the strength of the perturbation, and the system gets trapped into this kind of mean state, which is not good to compute the scale common generating function. This is the green line, and you already see that this is bad. Okay, so I have no idea why this increasing the noise has trapped my system in this situation, in which, by the way, you have a heat wave and you have a strong anticyclone over this part of Europe, but then there is this whole part of Europe that is very cold. So overall, it doesn't work for this target area. I have to see. This was just to show, it was just not to try to oversell things, just to show that this is a very preliminary phase and there are a lot of problems, and this, I'm fully aware of this. But I'm happy that I get these curves. I mean, I wouldn't expect to get them so nicely.
It might even depend on which degrees of freedom you put the noise.
Sorry?
It might even depend on which degrees of
Absolutely.
freedom you put the noise.
Absolutely. Absolutely. And in a system, in a multidimensional system with this, with a lot of variables, it's impossible to do a complete sensitivity. The other thing is about the cloning time. Do I have 5 minutes? Okay. This is about the cloning time. I still have to make experiments on changing the cloning time, but this is just to show something obvious, so that this system is very different from the unstable Lebesgue process. The cloning time, choosing the right cloning time, basically has to do with how the trajectories separate when you put some noise in this system. Okay, so here I've done a simple experiment in which I've taken 3 initial conditions, one representative of the average state of the system, one very cold, one very warm, and then I've run, not with the population dynamic algorithms, the normal simulation of the system, an ensemble of trajectories, adding a little bit of noise. And okay, you see that then eventually they relax on this is the average, the ensemble average, and this is the ensemble variability. You see that in the end, of course, I mean, they relax on the stationary state, but if you look at how the standard deviation of the ensemble variability measured as a standard deviation of the variable among the members of the ensemble evolves with time, of course, you have the things separate exponentially at the beginning. What I wanted to just to show, and in the end they relax on a value that is the standard deviation of the stationary state, but the thing I wanted just to say is that after one autocorrelation time, which we are about here, we have about 0.1 of standard deviation, so it's about 7–8% of the standard deviation of the natural variability. In the unstable Lebesgue process, after one autocorrelation time, this already accounts for 90% of the natural variability. So the properties in terms of separation of trajectories between the two systems are completely different. So there is no reason to think that the optimality of the autocorrelation time for the Ornstein-Uhlenbeck process should be valid also for my system. I've taken as a first guess, it has worked, luckily, not too bad, but we have to do sensitivity on this, absolutely. And this is it, essentially. So the conclusion, as I said, these are preliminary results. I just wanted to have a look at the fact that it makes sense to do these things, because otherwise I don't spend more time on it. Okay? And to me, what we have seen is that it makes sense. There is still a lot of work to do in understanding the properties of the algorithm, in understanding which is the optimal way to apply it to this system, but there is potential to work on these things. Yeah, and what I'm happy about is essentially that I'm getting that the average of the bias dynamics is this thing. Okay, remember this picture? And heat waves and composite average over the heat waves look like this. So qualitatively, the pattern is very similar. So it seems that I'm getting the right dynamics to increase, let's say, the probability of having large fluctuations of the control variable. So what to do next? In the short term, doing sensitivity, essentially. Okay? Recalibrate better which control variable I take and do sensitivity on the parameters of the model. In order to go more in the physics, compare the statistics of blockings. There are several indexes, in particular the Tibaldi-Molteni index, and in the meteorological literature, blockings have been studied a lot. There are indexes that they are basically based on the gradients of the geopotential height along the meridional direction, which tell you the frequency of occurrence of blockings, the lifetime of these events, and then to check also the correlation of these events with the anomalies of temperature. To check that in the bias dynamics, to check that in the normal dynamics, and to see if indeed I'm increasing the frequency, if I'm increasing the lifetime, if I'm increasing the correlation with the temperature anomalies, and then using those formulas to see if indeed I'm able to give better estimates with a smaller variance of these statistics using the bias dynamics. And in the medium long term, there are a lot of questions to think about. I mean, first of all, the fact, as I said, I mean, the large deviation limit is not for this individual heat wave. I'm just pushing the system to realize large fluctuation for a very long average, for an average of a very long time of the control variable. I'm forcing it to create a train of these events, hopefully. I have to check, but this is my idea of what's going on. Is this really useful to compute better the statistics of these individual events? I don't know, I have to check. And can this be used to improve the understanding of the physics? So making the computation of correlations between certain fields to the occurrence of the blockings with the correlation with the surface temperature to understand what is the physics of the system during these events. Is it better to study it in the bias dynamics? I don't know. We have to see. The guess is that this is the case, but I don't know. We have to see. And then what about trying other observables? And there are other observables which could be better suited to be studied in this way. Heat waves are nice because they correspond to very specific dynamical patterns, and this should make things easier. But there are things like precipitation that have other advantages. In particular, precipitation is basically memoryless, so you don't have the problem of having autocorrelation time of 1 week. Daily precipitation is basically decorrelated. And there is an interesting thing that the amount of precipitation is decorrelated, but if the occurrence of precipitation, so if you make a synthetic time series of 0 ones when it rains and when it not rains, these are a very long autocorrelation time. So it's a bit of a strange observable, and it could be interesting to study it with this kind of algorithm in a different setup. In particular, there are a lot of models in the literature that have been developed which are basically stochastic models, just basically stochastic differential equations, that are used to basically to fit observations in certain places, and sometimes they are also done like in a network. so that then you can have correlation between precipitation in different stations. And these are often used to study extremes. And this would be a very natural environment for these methods, because then I don't have the huge computing time of a GCM, and the system is stochastic, so I don't have the problems of having a deterministic system. So it could be worthwhile to work on that a little bit. Let's see. As I said, there were very preliminary results to show that it could make sense to think to apply these methods to this kind of problems. I'm honestly, personally optimistic. There is a lot of work to do, and actually, if people from your community who are the developer of the method have some idea or have arguments to tell me that it's not the case, actually it's crazy to try to do that, please do. Thanks.